not telling the truth, because as long as we cannot calculate such fundamental nuclear reactions ab initio, we simply don't understand the standard model with all its consequences. That's why these methods are so important. They allow a direct mapping of the symmetries of QCD on these hadronically QCD photons, nucleus, and pions, and this allows us in detail to study the structure and interaction of these nuclei. And as I showed you, we can then also really ask very detailed questions about fundamental parameters. And of course, one has to now do to repeat this calculation, extend them to the whole chain of element generations, which requires more work. But in principle, it's possible that one can now map out the whole element generation chain as a function of the quark masses and electromagnetic fine structure constant, get even further stringent constraints on that. That is work in the future, and I hope that you all had a bit of entertainment by this talk. Thank you.
Very much. Are there questions?
So now, you know theoretically that this whole state can be predicted. So local shell model can actually change to calculate this, or is it intrinsically difficult?
No, the local shell model is intrinsically difficult because this is a general problem with shell model. If you have a shell-like potential, then it's very difficult to put in clusters in there. If not impossible. The clusters, they are moved up to very high splittings. In principle, if you have infinite computing time and take all the shells, of course, then the state should move down. But in practical purposes, you would have to add something to the local shell model to account for this clustering by hand.
So it
works well. It doesn't work whenever you have alpha particle clustering, the local shell model is for any foreseeable future not able to get this correct.
It looks like all other spectrum comparison with data.
Yes, because the clustering aspects play no role for the other ones. It's exactly, you can exactly pinpoint where it fails or will fail, and that's where it fails. This was essentially known before. I mean, it was clear that, you know, there have been cluster models for the whole state that people just fuse alpha clusters and get already decent description. And in this stage, they're never compatible with the shell model because you cannot get them in the shell model. And this is clear because these correlations, if you look at something like a 4-nucleon correlation in the shell model basis, it's very unnatural, so it pushed up in energy very high. And it's clear that if you just look at a typical shell model basis, there's no foreseeable future where you have such big computers where you could store such configurations that you can put them down close to where they are. So they're somewhere, but they're so far removed that
it's difficult to produce this bent-to-arm configuration.
It's difficult for the shell model, yeah. But this is not something new. This is essentially known since the shell model has been formulated.
Other questions?
So I mean, the argument was always that the fine-tuning superficially is extremely severe because I can move the state by only 100 keV, and the total binding energy is 70 MeV, and superficially it seems like a part in 10 to the 4, or something like that. And so then part one is this kind of Weinberg argument that, well, maybe this is sort of dynamical. It comes from the fact that the states are clustered, so it's actually kind of natural for helium-4 plus beryllium-8 to be close to a state in carbon-12. Because one is 1 alpha, the other is 2 alphas, and the other one is 3 alphas. But in addition to that, we seem to find this sort of funny correlation that you have this band where there's some linear combination of these two derivatives, so the derivatives of the two scattering rates with respect to the pion mass, where there's kind of an extra correlation that somehow reduces the amount of fine-tuning. And this data point that you put into this plot is somehow accidentally close to that band. So is that really an accident, or do you understand where it comes from? I mean, within error bars, you seem to find that there could be no fine-tuning at all, roughly speaking.
Yeah, that's possible, yeah. The point is, this is in fact possible. And I mean, this was argued already by Weinberg in some talk he gave in 2001 or so, that he said it's all clustering by clustering principally preceded this correlation. So the point is on this, maybe.
But this is an extra effect, isn't it? That has nothing to do with plus. If you go to the next plot, the fact that this point with the error bars is close to that red line. That has nothing to do with clustering, does it? It's an extra funny cancellation.
No, clustering just means that you are somewhere on this curve.
Yeah.
Clustering just means that you are somewhere on this curve, but doesn't tell you where. So the clustering only tells you that there's this correlation, that if you change the k-factor for the alpha part, you move along
Yeah,
this
so
line.
clustering means that these three different bands are close to one another. But
They're
what
close to
happens-
one another, and they of course just depend on the k-factor of the helium 4.
But what happens on the next plot has nothing to do with clustering. It's an extra accident, isn't it?
Yeah, the point is that exactly this I didn't want to discuss. I mean, there's one number. So if you look at these formulas before, this is a new effect which you don't really understand so well. That you see that this divided by this is roughly the same as this divided by this, and that means that there's one particular value where essentially there's no more fine-tuning whatsoever.
Yeah. And we're accidentally close to that.
And yes, somewhat close to that, yeah. So it's not, the point is, you can only exclude this if you shrink the error bars here by, for example, lattice calculation of these inverse scattering lengths, which is in principle possible at some point. So that is something which is not yet, that's not really understood, or which you don't really know so well. So there's one particular value which corresponds to this k factor of helium 4 being 0. And we don't seem to be very far from that. So that is something, I don't know how to call it, fine-tuned clustering or whatever. That's on top of it, yeah.
But it's not actually fine-tuning, because in QCD it's completely predicted what this number is. It's not a function of some fundamental parameter itself.
Yeah, the point is that we are accidentally close to this funny point.
Yeah.
So that's something which... Okay, but the point is that one really has to shrink these error bars to see whether this is consistent with this point, but you could also be excluded once the error bars are smaller. They're just close, but you cannot say more.
Other questions?
My impression was that Hoyle actually was motivated not because he wanted there to be a universe, but because he didn't want there to be a Big Bang theory. So he actually failed because there is a Big Bang theory.
No, but this came later. I mean, Hoyle did many good and not so good things. I mean, before he came to cosmology, he was really doing network calculation in stars, and they predicted this state. He just put it in by hand to have this balance. And then later he came to the steady state. He didn't like the Big Bang, so he was promoting steady state. But this had nothing to do with his early astrophysical work.
Well, I thought that the idea was that he wanted to be able to make all the elements in stars instead of the Big Bang.
No, but this X process, that came later. That he refused to believe in. He invented some extra funny stuff.
Oh yeah, no, he had that. That's right.
So that came. This is decoupled. His earlier work was really good. And the later one, well, this was debatable, but he was a sharp mind. I mean, you can say, and so this had nothing to do with his later trying to get rid of the Big Bang.
All right, well, let's thank Wolf again.